Hi, everyone. Finally glad to be here. Been a long road to get on that stage. So I'm going to talk about serving highly dynamic content, as Matteo mentioned, to over 500,000 devices in near real time. To some of you, maybe a blip. To some of you, maybe a long road ahead. But what's so interesting about this story is that we didn't have any ramp-up time. There was no traffic at all, and then next few hours, over 500,000 devices. So how did we get there and haven't failed? Going back to a little bit about myself. Overall, love programming. I'm a software architect and consultant. Currently, I'm a CTO at StreamLayer, but also a founder at Makeomatic, professional services consultancy. Here are my handles on GitHub or Twitter. Please follow. Need those followers. Okay, let's go to the topic. So, the context. For StreamLayer, we're doing interactive experiences during live events, which means it's near live stats, live polling, trivia questions, predictions, betting. Because of COVID, video chat, watch parties, social feeds. A lot of different patterns of usage. Most of all, it's extremely spiky. One day you could have no traffic, the other day it's through the roof. All the services have functionally various load profiles. For some things, you could have read-heavy stuff that's not frequently updated, and by not frequently, I mean every 5 seconds. For some other things, you could have like live polling or trivia. Everybody wants to see live results, and you have people watching a sports game. You run a poll, and then you suddenly have 500,000 people answering, and they all want to know how everyone else is doing. So really hard to actually write that stuff, calculate, send that back. That's why, well, near real life is important. How do we do it, or how do you generally do it? How do you scale from something small and then make sure it doesn't fall over? Those are 5 things that I'm trying to outline. There are obviously more, but those 5 are the most important. First one is the application runtime, right? Could be anything, and it's the first decision you usually make. For me, as you might have noticed beforehand, we haven't really had any CPU-bound tasks. And, well, Node is great at networking. Node is great at I/O efficiency. So beyond that, you really need to think about what are other criteria, right? For Node, well, it's the loveliest thing. It's also the great community, like everybody in here. Can we get a round of applause for everyone? Like, the ecosystem is just amazing. You can find anything on any topic, though not too much on audio processing, because I've been trying to do that in my free time. But we'll get there. It is constantly evolving. There is some competition. There is Dino, there is Bun. We're always progressing. It's extremely fast. It's easy to get into. It is hard to master. But anyway, long story short, we did select Node.js as our runtime, and you can select something else. Doesn't necessarily need to be that, but my talk will be about that. Keep in mind, like everything I'm talking about, the roots of this is happening 4 years ago. So a lot of things are relatively new. And the decision at the time was, how do we deliver content to our clients? And our clients, our users, as call them, are mostly native applications, and they're written in different languages. So we had a dilemma, whether we go with a classic transport, use RESTful APIs, then thinking about doing live updates, we'd have to either use WebSockets or something else. And at the time, gRPC was starting to get traction. This is a framework, and it stands for Google Remote Procedure Calls. And, well, it was relatively new. It was released just 2 years before that. Had some support, but it promised great efficiency, high throughput, low latency. It was primarily used over HTTP2, which means we can interleave requests, we have multiplexing, We don't have a problem of head-of-line blocking, so we can use just a single connection for every one of our clients and do everything we want over this. So we really took a leap of faith there, but I think it paid off. This is a little bit more about gRPC, as you might not be familiar with it. Key points here are bidirectional streaming. That's the only connection you need to actually send data back and forth, and the throughput is just through the roof. The other thing that's also inherently great about it is Protobufs. There were talks about it before. Key point here is that it's a format to serialize or deserialize your data, essentially transmit it. You would use it instead of JSON, and it's extremely efficient. Also, using it, you can generate stubs for your clients in any language, saves you a lot of time. Next thing that we had to consider, and also mind you, that was 4 years ago, is that you can structure a code in a different way. And if you're small, you can always start with a monolith. You can modularize your code. There were quite a few of architectures presented here beforehand. And for the most part, you'd be fine. But as you grow, your team will kind of step on each other's toes, and it's often easier to maintain separate services. So we decided to go not with the microservice, but with a microservice configuration, in a sense that we have functional modules. There are not too many of them, but they're all separate, and they need to communicate with each other somehow. They also need to communicate back to the clients that connect to them. So how do you decide what to use for inter-service communication? One easiest thing to do is just, well, have your last mile transport connect directly to your services, and then somehow figure out how they connect with each other. You can use Mesh for that, but tech wasn't really there back then, so other thing existed, and it existed long before then, and that's message brokers. In our case, we selected RabbitMQ foremost for its inherent ability to process everything in memory and also scale. You can have cluster as large as you want and process billions of messages per second, and be very happy about it. So beyond that, also a lot of great choices, for instance, such as Kafka, that is widely used, but it is using the disk and wasn't the best thing for us at the time. Key takeaway here, just weigh in on what your requirements are, what's important for you, and then you can select the right tool for the job. One of the next things, load balancing, right? Just talked about it. Don't connect to your Node.js server directly. You'll have problems. This is where we have specialized tools come in: Nginx, HA Proxy, Envoy, Ambassador, Traffic, and I think a dozen more different ones. They constantly pop up. I think a new thing from Cloudflare is soon to be released as well. Key point here, this is the entry point into your backend infrastructure. This is where all the connections are gonna come into your system, and it needs to be very efficient. It needs to be able to scale both vertically and horizontally, in a sense that you need to spin up more instances, but also it needs to be memory efficient and needs to utilize many cores. Otherwise, you will fall over. So 4 years ago, we selected Nginx as kind of a tried and true thing. One key thing we didn't account for is that gRPC support was relatively new and still not fully baked into it. I don't know if you know or not, but the main difference between the classic HTTP1 and HTTP2 is the multiplexing, right? So what happens is that you have one connection, you have many requests going over it in HTTP2, and in HTTP1 you just have many connections if you need to have requests going in parallel. There are, of course, subtle things you can adjust in the older protocol, but we'll not go into that. And so what happened to us is that 20% of our clients, again, the Pareto principle, they were producing 80% of load. And the other 80%, well, they were mostly idle. Why does it matter? Well, because by default, load balancers will balance using connections, which means Some of your servers at the back will get connections that produce all the load, and some of the servers will get connections that don't produce any load at all, which will unevenly load your servers. They will stagger and essentially fall over. So what to do about it? You can use mesh, but in my opinion, it is a little too complicated unless you really, really need it. Like you want to have mutual authentication of every node. You want to see where your traffic goes. That's a great tool for observability, but doing a full mesh, it might slow you down. So like really think before you do it. What we did is we used Linkerd. It's a sidecar, essentially process that runs next to your entry point gateways of the Node.js and your load balancing. What it does, it makes, well, it is gRPC aware, and that's why it's so important for us. It starts balancing based on the streams inside HTTP2. So whenever your clients do requests, it's not like the proxy is actually aware, and you get 100 requests from one client. Those 100 requests will go to different servers. We're happy. And if you need all of them to go to the same server, you'll open a consistent stream, and it will be kept open, and then that's another story. But you'll no longer face that issue where your servers are unevenly loaded. Databases. Last but not the least, there are many, many different architectures, many, many databases. You can even start with nothing, really. Just use SQLite. For many cases, it will be sufficient. But takeaway here is there is no right answer, or rather no silver lining here. You can't select one database and expect it to perform great in any variety of tasks. You need to understand what your load profile is. Let's say we're talking about stats. It's updating not too frequently. Usually it's from a human input somewhere on the stadium. Then you get the data, it is saved to the database, and then you need it to get it to the clients. You have live updates, sort of, but also it's changing like every few seconds. So if you have a lot of clients, you may just save that information in the in-memory database, such as Redis, and retrieve it. It'll be an append log, essentially, and you just feed it to all your clients. Those who come in instantly, you can cache that data and just serve it from the edge, also reducing latency and load on your database. On the other hand, if you're very read-heavy, such as the case with polls, where you have hundreds of thousands of people submitting answers to you, and you need to keep track of those answers, not to allow them to vote for a second time or change their vote, or you want full visibility, you want to be able to send the results back to all of those clients live, you need some sort of a different database. Or you need to come up with clever solutions on how to make it seem like it's live. For instance, do updates every second. Just calculate, aggregate, and send a snapshot of what the results are every second. Nobody will notice because, well, I mean, who knows if you're updated every second or every half a second. Doesn't matter. So perception is also very important when designing things. Then, this is what we ended up with. From all the components. It is sort of simplified on the middle of pieces regarding observability, tracing, and whatnot, because it's not very important. We have clients, they talk with gRPC to an entry proxy. We have web that does some moderation work. You might notice that it says gRPC web, and that's because browsers can't talk using gRPC protocol by default. The reason for that is there is not enough visibility in the networking stack to allow that. So to have browsers talk using gRPC, you actually need a proxy in between which will translate what browsers can do to an actual gRPC protocol. Then you have the load balancer, then the gateway. In our case, this is where all the gRPC connections are going to. We terminate them there, distribute requests using a message broker, and then each microservice handles its own thing, and then it's all aggregated, and, well, you can send information back. Thing is, would it actually work? Right? Started 4 years ago, no traffic, designed for scale, but how do you prove it? Like, I mean, where do you get the clients to test your thing? Nobody wants to be a guinea pig. Well, maybe it works. I know of 3 ways to do it. right? First one, Leroy. And then, well, you deploy it to production, you get traffic. Maybe you work and maybe you don't. Don't suggest that. But if there is no traffic, maybe you can try it. 2 ways to go about it that actually work and don't put you under too much liability. First thing is observability. We talked about it a lot in the previous couple of days, so I wouldn't go there too much. But in a JS instrument you code, make sure you can see how your requests are performing. Make sure you record that. Check the outliers, why some things are taking much longer. Determine which services are slow, and then investigate further. That would only work if you, let's say, it would only work as a starting point if you can gradually ramp up your traffic from small amounts to higher amounts, so you actually have time to fix things before they become an issue. The other way is to load test everything, and this is what we did. To load test, you need to, well, let's get to the next slide. You need load producers. What's important here is that your load producers need to be able to saturate your system. Because if it's not saturated, you don't actually know what your boundaries are. You don't know what your constraints are. You don't know when it's going to fall over. You start small. You test every component of your system. You test it for the maximum throughput. And it is a baseline for each of your components. So in our case, if we go back here, we would test each database and its maximum throughput for writes, reads, and then mixed loads. We would test message broker. We would test gateways. We'll test everything separately, but also, and most importantly, we'll test everything together. But you need to know the baselines to understand which piece of your system will become a bottleneck to then eliminate it. Some of examples of load producers. gRPC, even though it's much more mature at this point, there are only 2 good things that I've found and used. These are GHZ and Pandora. Pandora is a thing written in Golang on top of Yandex Tank. For HTTP, many more things are available. Autocannon is the one I love. Shout out to Matteo. Yandex Overload is a little bit more complicated, but it has a great visual interface if you want to go into details. Apache JMeter is a little bit older, but also has its place in here. As we've selected RabbitMQ for our message brokering, we do use this. Every other system would have its own thing. You can't really use one for the other, but you can determine the baseline of performance using that. Initially, I wanted to talk about specific databases and what we did to optimize their performance and how Node.js talked to them. I have literally no time to do that, so just look at the PG bench. This is the simplest tool. It's bundled with Postgres. You can determine your database throughput and work from there. And then another database we use is ClickHouse. This is for analytics storage. Extremely efficient. People who love Elasticsearch would love this because it's much simpler to manage and it scales way better. But it's primarily for analytics. You don't use it for full text search. So if you want that, use something else. Now let's go back to Node.js because it's all about it. Once you produce enough load, you need to see what's happening inside your system, right? Well, you determine, for instance, that your web server can handle, I don't know, 10,000 requests per second. Do you think it's low, it's high? I don't know, it doesn't matter, because it's all about your business logic. The thing is, if you need it to be higher, you need to understand what's slowing you down, what's unacceptable. Because maybe the throughput is great, but your latency is not. So how do you fix that? Use the tools for profiling, and then that will help you to determine the root cause of an issue. And again, Clinic.js, super great tool. Shout out to everyone who participated in the development. 0x used inside it. This is for visualizing flame graphs. And then if you just want to use the built-in tools, the Chrome Web Inspector, you can get heap snapshots, CPU profiles, and then work with it there. Now, well, live demo time. I actually prepared a lot of things beforehand, but, well, it's mostly live. Let me swap. One second. Yeah, okay, great. Okay, what do we have here? It's too small. Yeah, right. So I've prepared 2 servers, web servers. One using Fastify, we'll love it. Oh, why is it not? It is lagging like crazy. Okay. Demo gods are not with me today. Retina is too slow. Okay, maybe this works. Okay, not showing you the code, but you'll gotta trust me. Anyway, one thing is we'll start Fastify. Does nothing, just returns the string it was given, and we'll test it. I think that's the command. Yeah, so I'm using autocannon, just sending requests, get requests here. Takes 10 seconds. Pretty fast, 73,000 requests per second. Main point here is there is no latency, almost no latency. Well, sometimes GC kicks in, but, well, on average, like 99%, there was no latency at all. Key takeaway. Do not trust the results on your dev machine. You see like big numbers in here, that's not going to happen in production. Your machine is great, but if you're working in the cloud, if you get like results that are 5 times slower, well, be happy about it. That's already great. Now, another thing, gRPC. I use TypeScript here. I want to show you protofiles, but it's lagging like crazy, so maybe I'll try to do it again. But after. So gRPC has the concept of streams, right? No. I'll test. Okay. I'm using JHZ here. This is a little bit longer syntaxes. You have protofile, which describes your services. This is essentially like the path you would query. Oh my God. 1 second. Okay, I did 300,000 requests over 1 connection. Like the results are here. Much slower, right? 24,000 requests per second. But this is using essentially standard RPCs where you just send requests back and forth. Each time it will allocate a new stream, then it will deallocate it. Lots of GC happening. The latency is not too great, even though nothing is really happening in here. I really want to show you the code though. Yeah, right. You can see that probably. So that's what we're using. This is a unit request, and the protofiles for this were that. I'd be happy to talk more about it, how it all works, just not now because I have no time. Yeah, but let's go back to testing. There is another thing called BD streams, and that's what it's all about. Bidirectional streams are what's important. This is sort of an analog of WebSockets. You'd create a stream and you can send messages back and forth from the server as well without asking for anything from the client. And so as you can see, the result here is about 162,000 messages per second. And this is also still running on Node. What do I have here? So Node 18.10, latest release, it doesn't have a board controller fix yet. Yeah, pun intended. One more thing. I want to show you the clinic.js, because like now you've seen the baseline, but you don't know what's fast, what's slow, what do you fix? Do you need to fix anything at all? I don't remember exactly what I wrote yesterday. Okay, So we'll start cleaning JS, and we'll be capturing flame graphs. I'll do the same thing. I'll just send 300,000 requests, probably twice, so we have more data. It's happening, I promise. Okay, and once more. Almost there. Okay. Now I'm stopping this to get the profile, and well, here we go. This is what's happening when we're doing unary calls, right? And this is gRPC. White stuff is Node core. Yellowish thing is what's happening, right? Those are the main functions that are getting called, and this is the relative time that it takes for them to run. So once we get that fixed in the core, it'll be much faster. All right. But here, this basically gives you the idea of which function you need to look into to make things faster, right? So there is not too much stuff going on, obviously. It's a very small server. I'll try to do one last thing with BD streams. I want to illustrate why BD streams are faster and where the time is spent. Okay, so now you can see the abort controller is non-existent here, and most of the time we're spending in actually decoding and encoding the data, transmitting it back and forth, which means the overhead that we had from always creating new connections for one single request response is not so relevant. Right? In this case, I've opened, I believe, about 2,000 streams instead of 300,000. So you don't even see it on this flame graph. And so stream decoder, chunking, whatnot. Can probably optimize it, but not too much, because there is really nothing in here that sticks. Okay, I'll wrap up because I'm really out of time. Let's get back to, all right, so the end. Key takeaways, do not trust anything you see on the internet. Test everything yourself before going to production, or rather, as part of your development process. Establish those baselines. Don't do testing just once. Maintain load tests. Perform them each time you make a new release. Make it a habit. After that, your code will be much better, your services will perform much better, and any unexpected spikes in traffic, it won't be a problem for you. So thank you. Follow me on Twitter. Talk to me after the session. I'm still around. Yeah, thanks.